Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today's topics of discussion will be based on item of week number 4 under the main topic of potential difference and energy density. But to be more precise, what we're going to discuss in this session going to be focused on this issue, the last part of the topic here as underlined, which regard gradients and energy within a system of charges. Okay, so as a summary or as an objective of our discussion here, we're going to focus on two main topics, which are the first one should be gradient and the second one should be energy within a system of charges. Okay, so before that, let's recap what we have actually learned until now. So let's recap because this is important, because you will see what we have discussed previously still relevant to what we're going to talk about in these sessions. So we are talking about electrostatic field, and we have learned, I'm going to use a black ink now to indicate what we have learned. We know that the source to generate electrostatic field are stationary charges, so we're going to represent them as rho v, known as volume charge density, and we know that this source going to generate the first field known as electric field intensity, and then second type of field we denote it as electric field density. So we learn to obtain electric field intensity from the source, we can adopt Coulomb's law, or we can find electric field density by utilizing what is known as Gauss' law. And after that, we learn about another layer of components generated by the source, and we denote that as V. And for us, V is something that common electrical engineers, which we call it as potential, and we know that V can be determined either from the E field or from the source. So that should be the detailed component what we have learned until now. So now we're going to talk about something new, so meaning that we're going to add more information on our overview diagram here. Later on, we're going to see more additional information going to be added on this particular overview graphical information. So what I'm going to do, I'm going to go to the title of our discussion as mentioned earlier. We call it to be known as gradient. Okay, so that should be our topic now, gradient. So to make it more relevant to what we are learning now, we're going to relate it to gradient of V. So that's what we're going to do now to make it more relevant to the thing that we are discussing. So the latest parameter that we talk about is potential. Now logically, I'm going to relate that with the topic gradient. So gradient of V, and our V here going to be known as potential. So what does it actually represent? So let's say we're going to plot a graph now. So we're going to plot a graph as the name of the topic now, potentials. And let's say we're going to plot with any parameter, let's say call it distance. So let's say our graph have this behavior pattern. Okay. So what the issue that we're going to talk about now is the gradient. So in other words, the slope of the graph. So meaning that let's say I'm going to talk about at this particular point, at this dot on the graph of V against, let's say, distance, and then we can see there is information that we can extract from the graph, which is known as the slope. And this is what is known as gradient of V. So what actually this slope contain? What information actually this slope have in order for us to use in many engineering applications, especially electrical design. When you want to design, let's say, PN junction, this is the important parameter people use in making decision. The slope of the V, not the value of the V, the slope of that V. So what does it contain actually? So that's what the issue that we're going to discuss. So to make it more easy for you to do your own revision, so you can read by yourself this information from our textbook. Okay, if you got the textbook. So this idea is mentioned page 149. If you refer to the Sadiku textbook as our textbook for this particular subject. And the section should be section 4.9. So, I mean, Sadiku do explain quite detail about the issue, but for me, I'm just going to summarize. Straight away going into the issue, what information actually contained by this slope of V against, let's say, positions. That's what we're going to discuss. So in order to do that, so it's easier for us to relate the discussion to examples that we have done before. So let's say we refer to our previous example. So refer to handout, I believe handout 5, which talk about Gauss law. So Gauss law. And then let's say be more specific now. Question number 2. I think some of you might recall this particular example. So what actually this question 2 about? Remember that we are given a source shaped as a sphere. Okay, I think you can remember that. And this sphere having radius A, and the charge involved in this particular problem known as surface charge rho s. So remember that particular problem? So you've been asked to find D in all region. So let's say, so using Gauss law, we have solved the electric field density generated by this particular structure of charge. Gauss law, remember, we define the region of interest. There are two regions, region number 1, region number 2. And then we have solution for region number 1. Okay, for region 1. Remember, what is the solution of our D? Anyone can remember? The D1 is equal to 1. Yes, equal to 0. And our E1 also equal to 0. Okay? And for region 2, we obtain the solution to be D2, I believe not equal to 0, equal to what here? Yes, rho s A squared over R squared in R directions. And since the medium of interest in this problem still referred to free space, so we have the electric field intensity E in region number 2 is given as rho s A squared over epsilon naught R squared in R direction. So I hope you can still remember this particular solution that we did together. Okay. Okay, so what I'm going to ask you to do now, let's plot. Okay, let's plot the graph of V against R, the radius of our shell. Okay, V against R. And we can see, based on our diagram here, the boundary that's separating region 1 and region 2 is R equal to A. So I'm going to clearly define this is my A value, and they're going to be a boundary here. Okay. And then what we're going to see, I'm going to use different color just to make it clearer. So for region 1, there's no electric field, okay, based on this result. But in region number 2, there is electric field, and we can see that the value of E is decreasing as R increase. So what we're going to have a spike here, then the field going to be decreased slowly. Okay, so that should be the result of electric field distribution of that charge structure. Okay, after that, when we talk about absolute potential, I hope that you can still remember from the discussion of absolute potentials. Okay, we obtain the V for region number 1 and region number 2. Anyone can remember that? From absolute potential, okay, we discussed together and we solved the same problem. We obtain for region number 1, V1 is equal to rho S A over epsilon naught. If you're not sure, please refer back to our notes or our videos talking about the solution of finding absolute potential for this structure. Okay, so we found two results, okay, V1 and also V2. So what should be the solution for V2? Anyone can remember? So the V2 that we obtained given as rho S A squared over epsilon naught R. Okay, so that should be what we obtain. So now what I like you to do, so please plot now the graph. Sorry, this one should be E just now. I'm very sorry about that. Yeah? This is the E. So now I'm going to go for the V now against R for the same structure. Okay, so now what we can do, there's still the same relevant boundary that's separating region number 1 and region number 2. But what we can observe in region number 1, the value of potential here is constant. Okay, what is the value of the constant here? Rho S A over epsilon naught. And when we enter region number 2, we can see that the potential decrease as R increase. So but the slope is slightly less compared to the above, more decrease, but here is less decrease because of the R term. So now this is the result from our previous example based on electric field intensity as well as absolute potential of the charge that have a spherical shape and the charge known as surface charge. So let's focus on our solution that we obtain. So let's go back to the title that we are discussing now, the slope of V. So let's look into this particular diagram. Okay, let's focus at this particular point. Okay, so the point here, And then if I ask you what should be the gradient, okay, I'm going to say to myself now, the gradient of V. Okay, what is the gradient? What should be the slope value at this particular dot position of the V graph in region number 1? And you can conclude that the gradient of V is equal to 0, okay, based on the slope of V at that point. And when we compare that to the actual same position on the E graph, we can see that at this point, the E is equal to 0. Correct. Okay, so let's test again at region number 2 now. So let's region number 2 here. So let's see, ask ourselves, what should be the gradient of V at this particular position? Gradient of V. So meaning that the slope here. And we can see the slope is not equal to 0 because there's a slope there. Okay, the slope is negative. And by comparing at the same value of R on the E graph, we can see at this position, the value of E is not equal to 0. From this observation, what we can conclude, okay, the conclusion that we can make from this observation is very simple, that we can say there is correlation, gradient of V when we compare to the electric field. So meaning there is the relationship, meaning that when the gradient not equal to 0, E not equal to 0, when the gradient of V equal to 0, E equal to 0. So that's what we can conclude based on the result we obtain. So we need that the slope of the V do inform us about the existence of electric field in that region. Meaning that when the slope is equal to 0, we can conclude there is no electric field at that position. If the slope of the gradient of V not equal to 0, we can say at that same position there is electric field. Okay? This is very important in electronic world, especially when they design transistor or PN junction. This is very important information to be observed and used. Okay, so this is what we conclude. I think that's not enough. So for us, we need to develop equation so that we can have more specific or more thorough relationships. Not only say, but with actual facts based on equation. So when we have, so the word gradient can be presented in mathematical term as this symbol. Okay, so that's the word gradient. So can be represented with this symbol. So whenever we have this symbol, so we know that this term is coordinate dependence. Meaning that the equation based on which coordinate system that we are using. Okay, so I'm sure some of you have seen this equation been discussed before, especially in mathematics engineering. So therefore, I'm not going to discuss, but I'm going to guide you where you can obtain the information about the gradient of V. So for those who have textbook, you can open to page 72, section 3.4. Okay, if you open to this particular section, you can read yourself about the model of gradient of V. But for us in EMT, we're more concerned about using it in the real engineering application. So we just use it rather than derive it. Okay, so therefore, for us, we know that the symbol given for gradient of V as such, and from the symbol itself, we know that this term is coordinate dependence, and then we know there are three different coordinate system. So therefore, when we dealing with Cartesian, okay, Cartesian, we should use equation 3.18. Okay, which section? Section 3.4. So equation 3.8 will relate this term to Cartesian coordinate. If we are dealing with cylindrical coordinate, so please refer to equation 3.19. Okay, that should be our second coordinate system. And then for the last coordinate system, which is spherical, please use equation 3.20. So that should be how we interpret gradient. Okay, for us, gradient have specific symbol, and then that symbol is based on coordinate system. Okay, what about the electric field now? So from our graph, the slope here is negative. So what we can say, the solution of the gradient of V should be the negative of electric field. Okay, that's what the way we relate the gradient of V to electric field. So this is a very important equation that we will use a lot in our problem. Okay, so that should be an important equation for us to utilize. So let's recap back our overview graphical presentation, what we have learned. Okay, this is what we have learned. Now, we've been informed, if we know V, we can find E. So that's what we've been informed now. How? By using this equation, the gradient of V equal to negative E. So this is the step that we add on our overall graphical representation of electrostatic topics. So we add new information here. By knowing V, we can find E. Before, by knowing E, we can determine the V. But from this issue that we discussed just now, we can now have the reverse process. Given V, we can find E. Okay, so let's do one example. And the example that we're going to do will be based on handout number 7. Okay, handout number 7. Hope you can see the problem. So handout number 7 should be the things that we're going to discuss. And I would like to focus on question number 1. Okay, so let's read it. So given V equal to this lengthy equation, but unit volt, so we know that the V here is voltage in free space. Okay, so meaning the medium that relevant, the parameter that relevant that for us to use is epsilon naught, free space. Okay, at P given as 2 minus 1, 4, from the variable given here, we know that the coordinate referred in this problem is Cartesian because magnitude, magnitude, magnitude. Okay, the first question, find V. Okay, so let's do it. Handout number 7, question number 1. So V given as 2x+ 1 square y plus 2 square, z plus 3 square. Okay, so for question number part A, so what is the V at position 2, -1, 4? Okay, so I think it's very simple. What you need to do here, just need to substitute x with 2, y with -1, and z with 4. Then you get a value. Okay, that's done. Just substitution with the relevant variable of x, y, and z. So you just need to do that for part A. Okay, so let's continue. So we're going to go for part B now, find E. Okay, so now a bit tricky now. For B, find E. Cool. So now what's important now, what information actually we have? So we know V. So that's given by the question. And what we want to find now, we want to find E. Okay, so what should be the logical step that we use based on our previous discussion? Good. So we know that this can be solved by using formula grad V equal to negative E. Okay, so how we should proceed now? So, and as mentioned, the symbol here is based on what we call it Cartesian coordinate. So now, from equation that we mentioned just now, 3.18, okay, so from equation 3.18, it said that the grad V equal to dV over dx x directions plus dV over dy y directions plus dV over dz z direction. That's what the formula of gradient of V looks like. Based on which coordinate system? Cartesian coordinate system. So what we need to do now, we have to solve the mathematics. How we solve the mathematics? So we have to substitute the V with the V here. So all the V in this equation need to be substituted with this V. So I have to substitute V in this particular term, V here and V. So in this particular term, then I have to differentiate the V with respect to X. For this term, V with respect to Y, and this term V with respect to Z. So when you do that, what you're going to have should be given as, so for X plus 1, Y plus 2, Z plus 3. Okay, that's the differentiation, and please add the term direction X. Okay, that should be the first differentiation. Then you repeat for the second differentiation here. With respect to Y now, it's going to be 4 X plus 1 square Y plus 1 Z plus 3, sorry, Y plus 2, sorry, square, and please don't forget to add the direction Y. And finally, for the differentiation of the third term respect to Z, what we're going to have 4, again, X plus 1 square, Y plus 2 square, and now should be Z plus 3, and again, don't forget to add the direction Z. Okay, so that's the differentiation, just solving the mathematics. But what we've been asked to solve here, find E. Okay, so the E, as you can see, based on the equation that we derived, should be negative of the gradient. Okay, so what we need to do, so the E should be equal to the negative of grad V. And please remember, at point P, okay, the X must be substituted with 2, Y with negative 1, and Z with 4. So therefore, you're going to obtain the solution. So you need to differentiate first, then only substitute. You cannot substitute and differentiate, because when you substitute, becoming constant. When you differentiate, therefore the result going to be 0. So you have to remember that you must substitute V first, then differentiate. After that, only you substitute with the position P variables. So that's the second part, how to obtain the electric field using the new equation we derived together. And then, but remember, don't forget to add the negative, okay, because the negative is important. If you forget to add this symbol sign, your solution will be inaccurate. So therefore, that's done. Okay, let's go on to the last part now. Okay, the last part want us to determine what is rho V. Okay, so the last part question asks us to find rho V. Okay, and rho V known as volume charge density. Okay, let's refer back to our diagram now. So we want to find rho V. Okay, find rho V. So to find rho V, we know that this can be done by using this equation, Maxwell equation number 1, divergence of D equal to rho V. So that's going to be our approach. So what we have to do, first we need to convert the solution that we obtained, the D, to become E, using D equal to epsilon naught E. Why we see this term to be true? Because the medium given by the question is free space. So therefore, this equation is valid. So from the E that we obtained just now, we can determine the D. From the D, by using Maxwell equation number 1, we're going to find the rho V. So that should be what we should do in order to solve this third problem, finding rho V. Okay, how we find rho V? By using this equation, and we call this equation as Maxwell equation number 1. As you can see again, this equation have del notation, and this term as well is depending on which coordinate system. As we all agree just now, the variable, the coordinate system that we are using in this particular problem is Cartesian. Therefore, we must choose the appropriate Cartesian coordinate system for the divergence of D. So based on the Cartesian coordinate system, you use C is going to end with this term, D dx over dy plus d dy over dz plus d dz over, sorry, this dx, I'm very sorry, old man already confused. This should be dy, this should be dz. Okay, that should be the correct equation. D dx over dx plus d dy over dy plus d dz over dz. So therefore, what we need to do from our above equation that we obtained just now, we have to first find d equal to epsilon naught E Then we need to substitute the dx by taking only this term only for dx. So what we're going to have here should be negative. I'm going to put epsilon naught first, then bracket. So, and then what we're going to have when we differentiate this term with respect to x, good, it should be 4. And then y plus 2 squared z plus 3 squared. Okay, that should be the first differentiation with respect to x. Correct? 4. This one end with 1. This one constant, we just leave it as it is. Yeah? Okay, how about the second term now? Okay, this should be our dy, sorry, ey, so dy should be multiplied with epsilon naught. So I'm going to add here 4 x plus 1 squared z plus 3 squared. Is it correct for the dy over dy? And finally, it's going to add again the third term here going to be our dz component. We just need to differentiate, going to be 4 again, x plus 1 square, y plus 2 squared, and then here when we differentiate respect to z, it's going to be n with 1. So therefore nothing appears. So this should be our final differentiation term using the model. Then what you need to do, so rho v at p position 2 minus 1 4, we just need to add from this term the x should be equal to 2, the y should be equal to negative 1, and the z should be equal to 4. So that should be the approach now. Okay? So now you can see what we learn actually they're interrelated. Okay. The issue that we learned about charge we've been discussed in week number 2, and then we are talking about the potential we discussed in week number 4. So everything are interrelated. That's what for those who are have the attitude procrastinate in their study, they're going to have real problem learning EMT. For EMT, you need to always be following the steps of learning because they are interrelated. You cannot miss it because that's going to be bad for both of us. Okay, that's done. So now, alhamdulillah, we have completed one example of handout number 7. I'm sure you can try other question by yourself, and then the only issue here just the mathematics, but the idea is clear. Only the mathematics that might be cause problem to some of us, but the idea should be no problem. Okay, I'm going to go to the next level now. So the second issue about energy stored. So energy in a system of charge. That should be what we're going to focus for the second topic. So what we're going to do now, let's say you have a charge distribution as shown, meaning that you have a charge distribution given in this red box. Okay, and we have 3 different charge. So I'm going to focus on 3 different point charge. So I'm going to recall the first point charge to be Q1. Okay, the second point charge, let's say we call it to be Q2, and the third point charge going to be Q3. And the question, how actually we calculate the amount of energy contained by this system? Okay, that's what the issue now. How much energy this system has? Okay, so to do that, you can refer by yourself. Okay, for those who want to find how it been derived, please go to page 156 of our textbook, section 4.11. So Sadiq could discuss about the derivation in detail. For me, I'm just going to explain how we actually calculate the energy in this particular system. Okay, for point charge, I'm going to write it clear. For point charge, okay, so I'm putting charges now, because many charges. So the amount of energy contained by the system given by WE equal to half, because it's discrete, I'm going to use the term sigma I from 1, how many point charge we have in the system? 3, so from 1 to 3 should be Q I V I. So we ask ourselves, what is the Q? Q is the magnitude of the charge, the magnitude of the point charge. And the V is the absolute potential. Okay, so therefore the Q is the point charge. If I'm referring to port Q1, so that should be my Q1. And what should be the potential? The potential at this particular position. So the V going to be referred to the position where we are focusing for Q1. Then we call that V as V1. And for Q2, the V that we are focusing here is known as V2. And for the V we are focusing here is known as V3. So that should be the way we interpret the equation. So in other way, if you want to actually solve the problem, we're going to say it's equal to half. And then we're going to sum it to be equal to what? Q1 V1 plus Q2 V2 plus Q3 V3. So that's how we do it. And logically, you can see if the number of charge increase, so this term going to be extended further. Okay, so the more the charge, the longer this equation will be. So what I'm going to do now, I'm going to interpret what is our V1, for example. So this V1 is meant what here? So let's focus on that discussion now. As I mentioned just now, this V1 is referred to the position of Q1. So now the V1 is located here. And the V1 is known as absolute potential. And from the definition that we solved, from the problem we solved regarding charge distribution last time of handout number 6, so we can say V1 is the potential due to which charge? Yes, Q2 and Q3. So therefore what we need to do, we need to derive the distance now. So the distance between Q1 and Q2, let's say equal to R12. The distance between Q1 and Q3, let's define to be R subscript 1, 3. So what we should do, then the V1 should be defined as Q2 over 4 pi epsilon naught R12. So that should be the potential here due to this source. Remember the absolute potential we discussed regarding point charge, where the reference of absolute potential is infinity. Okay, that's the equation that we are using. And then we're going to add, because there's another charge exists that affecting the potential here. So that should be Q3. So that's going to be Q3 over 4 pi epsilon naught R13. So that should be our V1. Okay, and you can do the same with V2 and V3, so you're going to have a nice distribution of equation. So then you substitute the value of the Q and the distance, then you're going to determine the total energy stored by the system of point charge. Okay, that should be the way. Okay, so, but we know in respect to the source of electrostatic, it's not only due to the point charge, is also due to the continuous charge. So now I'm going to rewrite the same equation but for continuous charge now. Okay, for the case for continuous charge. Okay, remember continuous charge can be defined either line charge, surface charge, or volume charge. How do we determine the energy stored? So we just need to rearrange the original equation that we saw before. So half still there, but the sigma that applicable for discrete point charge need to be changed to become integrate because we are dealing with continuous. Then the V, now the V is not volume here, the V is based on absolute potential, and the charge is represented by the sample dq. And then logically as well, if we are dealing with the line charge, the dq need to be replaced with rho L dl. And if we are dealing with surface charge, the dq need to be replaced with rho S ds. And finally, it can be for the volume, we need to replace the dq with rho v dv. And we can see here, the issue we discussed in week number 1 still relevant. Okay, so therefore that's what EMT, as you can see, they are interrelated. You need to always be aware because anything new still referred to old stories, the thing that we have learned. Okay, that should be the first method that we can use to determine energy stored in a system of charge. And I split into two types here. One referred to point charge, another one referred to a continuous charge. And we're going to do example based on the continuous charge later on. But another method that you can use to determine the field, the energy stored is from the information of the field. Okay, so let's say this equation we're going to define as equation number 1. So another method that we can use, you can use this equation, WE equal to half integration of D dot product E dV. So this equation number 2. Okay, as you can see, inshallah, both methods going to end with the same results, but you are given two choices to obtain energy stored in a system of charge. And by the way, to derive from 1 into 2 have been shown by Sadiku in his textbook in this section. So the derivation here have been proven by Sadiku. So I don't have to prove to you here. I just need for you to be aware where you can find the information of the derivation from equation 1 to equation number 2. Okay, that should be the final issue that we're going to talk about for today's session. But we're going to end our discussion with something that familiar to us, a problem that we are common already with the problem. So what problem is it? So going back to our problem that we saw earlier. Okay, let's say you have this structure. What structure? The one that we referred just now. A spherical structure having charged surface of sphere radius A. Okay, so the question says determine WE, or in other words, what should be the energy stored in this system of charge? Okay, so how much energy this system contains? And you can see this idea is relevant, especially those who want to determine how much energy is stored in your handphone battery. So this is relevant to that issue because handphone battery stored energy. And the way people determine the energy by using the what we are discussing now, the issue that we are trying to explain now. Yeah? Okay, so how many methods that we can use to solve this problem? Two methods. Okay, equation number 1 and equation number 2. I'm going to use both methods for this particular problem. Hopefully, at the end of the effort, we're going to see both methods will end with the same solution. Okay, that's the idea now, just to prove. But by the way, you can choose which one you prefer. Equation number 1 or equation number 2. Okay, so I'm going to use equation 1 now. Yeah? Based on equation 1 now. Okay, so it said here, dW, I'm going to use this term now, equal to half V dQ. Okay, so whenever I see this term, dQ, I'm going to represent that on my diagram. Okay, so this my sample. So my sample of what? Sample of charge. And based on the problem, we know the charge is a surface charge. Therefore, the sample can only be located on the sphere, dq. I cannot take sample other than that because I know in this position there's no charge. Similarly, at this position also no charge. Therefore, the only logical way for me to represent the dq in the equation by showing a sample on my charge, and it should be this term. And based on our experience, this should be defined as rho s ds, remember, because surface charge. And also based on our experience again, the ds should be based on spherical coordinate, should be equal to what? Good. A squared sine theta d theta d phi. There you are. Okay, so everything comes from experience. So it's nothing new. It's nothing new, meaning that you have seen it before. I'm just reuse it again. Okay, so that's done. So I have represent the dq to be here, and using my previous model, I can substitute the dq with this mathematics now. Okay, how about the v? The v is known as absolute potentials. When we talk about absolute potential, we know that the v must have reference where? At infinity. Okay, and then we have solved problem for the v. Remember, in region number 1, region number 2, so the v must refer to this position. Okay, let's use that now. Okay, so my WE now equal to half, and then I know that my integration now going to be double. Why? Because this theta and this phi. The v obtained from our absolute potential solution that we just discussed recently should be equal to rho s a over epsilon naught. That should be our v. Okay, remember the V1, V2 that we discussed earlier regarding this problem? So that's for the V here must be equal to the V that we referred just now, the V at the boundary. Just want to show you how I define the V that we obtain here. So what's the V at this particular position? Yes, rho SA over epsilon. So therefore, I'm going to substitute the V here, rho SA over epsilon naught. And that should be the way we defining the V. The V located at this position where the sample is being referred to. And how about the dq now? The dq should be rho s. I'm putting rho s. And then the ds should be a squared sine theta d theta d phi. And then the theta should be from where to where? 0 to pi, standard definition of the range. And for the phi, from 0 to 2 pi. Okay, I try to solve that mathematics. So the final solution, we're going to end with the unit joule. So that's using equation number 1. Okay, so for us that want to use equation number 2, okay, I'm going to write blue color now. Based on equation number 2, so what the equation appear to be, okay, WE equal to half the D dot E dV. And from our previous solution, we know that using Gauss' law, they're going to be two different value of D and E, correct? Okay, so therefore what we can say now, we see that this equation relate to electric field and also electric field density, intensity, density. And from our previous solution, we know that this structure have two distinct electric field solution. One is referred to region number 1, another one referred to region number 2. So since that is the case, we can now split the equation into two distinct regions. So I'm going to say first part will relate to region number 1 component. Okay, that's based on whatever field that appear to be in region number 1. So that's done. But remember, there are still field appear to be in this region. Therefore, we have to add them. Okay, half the integration of D region number 2 dot product with E of region number 2 and dV. Okay, and from our solution, we know that in region number 1, the D is equal to 0, and as well the E is equal to, so therefore the term of region number 1 contain no energy. Because why? There's no electric field. Okay, but there are fields in region number 2, therefore the solution will not be equal to 0 because there's still field in region number 2. Okay, let's substitute that. Okay, it should be half. Okay, triple integration now because volume. What should be the equation for D here? We know that should be rho S A squared over R squared in R direction, correct? That should be our D term. And for the E term, since we are dealing with free space, it's going to be rho S A squared over epsilon naught R squared in all directions. So that's for the E. And how about the dV? Yeah, should be R squared sine theta dr d theta and dV. That should be the dV based on spherical coordinate. So let's put limit now. Okay, the only field that we need to consider now, field of region number 2. Therefore, the R should be from A to infinity. So R should be from A to infinity. Okay, and theta 0 to pi, phi 0 to 2 pi. And then if you solve the mathematics now, dot product R dot unit vector R will end with 1. Okay, so give a try. Try to prove to you yourself that the final solution of both method actually should be the same. Okay, because that should be the correct answer. If they are different, meaning that something wrong with our solutions. So therefore, that should be the case. So now from these examples, you can decide which method that you prefer. You can use either equation number 1 or equation number 2 in order to determine how much energy stored in any system of charge. It can be any shapes, regardless, but yet the method going to be exactly the same. Okay then, so Alhamdulillah, we have completed issue regarding week number 4. So in our next lecture, we're going to talk about more practical application. In what sense I'm saying this? So the material that we use in our current discussion and previous discussion only based on free space. So which is not the correct approach, because why? When we look around us, there are other material involved as well. So that should be the topic of discussion in our next lecture. With that, thank you very much for your attention. Sorry about my maybe presentation today. So anyway, take care. Assalamualaikum warahmatullahi wabarakatuh.